Why do astronomers dedicate decades to creating countless maps of the universe? Those dots, filament-like structures, elongated galaxies, and strange rotational curves, which may initially seem like completely separate phenomena, are actually all pointing towards the same fundamental question in the energy filament theory. What does the large-scale tension terrain of this energy sea look like? Let's begin by looking at the cosmic microwave background CMB, often referred to as the baby picture of the universe. On the surface, it might appear as a simple map showing temperature differences of just 1 part in 100,000. However, from the perspective of the energy sea, it represents the distribution of tension in the universe at its very birth. Every area that is slightly tighter or looser was marked on that early image. It can be thought of as the tension base map from the universe's earliest stages. As time progressed over billions of years, the tighter spots on this map slowly collapsed to form galaxies, galaxy clusters, and cosmic filaments. On the other hand, the looser spots gradually expanded into vast, empty voids. As we discussed in earlier seasons, black holes often cluster in these naturally tighter regions, deepening them and shaping the small fluctuations on the original tension base mapped into the tension skeletons we observe today. When you observe the cosmic web in large-scale structure surveys, the long filaments, massive walls, and expansive voids, you can directly interpret them as the early tension base map that has been magnified and deepened over time by black holes and other cosmic structures, ultimately forming the mountain ridges and valleys we observe today. Redshift surveys provide the height scale of this three-dimensional map, adding depth and distance markers, helping us visualize the varying dimensions of these cosmic features. Then we move on to the weak gravitational lensing shear maps, which gives us the slope direction. Distant galaxies appear as small grids stamped onto an elastic sheet. As this sheet is stretched and sheared by the tension fields, the grids elongate in specific directions. By analyzing these small distortions, we can reverse engineer the direction of the slope, effectively determining which way the hill is inclined. Next, the rotation curves show us how steep the slope actually is. The faster galaxies rotate at their outer edges, the steeper the tension slope they are navigating. The steeper the slope, the more unusual the orbital speeds become. By piecing together all of these observations, we start to get the full picture. The CMB provides the early tension base map. The large-scale structure and redshift surveys outline today's valleys and ridges. The shear maps indicate the direction of the slopes, and the rotation curves reveal how steep those slopes are. When combined, all these measurements create a massive contour map of the universe's tension field. Astronomical observations are not just about counting stars. They are part of an unprecedented effort to measure the cosmic field, attempting to map how this energy sea has been compressed and shaped and how its skeleton has evolved over the largest scales. Tap follow, share it on New Physics, Clear Universe.